Hey scholars, welcome to chapter 18-2 where today we're looking at what are the major outdoor air pollutants and what problems do they cause as far as human health goes, since that's what we kind of talked about with the last chapter. So one of the things we have to first do is define air pollution, and that's the presence of chemicals in the atmosphere in concentrations high enough to actually harm some sort of living organism, ecosystem, or even a man-made material. And there are lots of different sources. There's lots of natural sources where like dust blown up by wind, pollutants from actual wildfires and volcanoes that can happen naturally, a chemical called VOCs or volatile organic compounds that are actually released by plants, and then also by withdrawing groundwater from the earth. So those are natural sources that can cause some air pollution problems. But the problem with it is that most of the sources that where we see the effects from are human sources, and those are mostly by industrialization or urban areas. There are two types of those. There's the stationary source, which is just industrial plants that are producing mass amounts of goods, and the mobile sources, the motor vehicles allowing people to transfer from point A to point B. So those are our two major human sources of outdoor air pollution. Let's take a look at air pollution from past all the way to present, where we're at today. But let's talk about the bad old days. And we've said that you've heard the term the good old days, where everything was perfect and pristine, but not necessarily in the case of air pollution. Actually, it has to even go back to when we first discovered fire and combustion. And in the Middle Ages, we had wood smoke over the urban areas. Remember, you've heard of those terms as the Dark Ages. And most of the reason why they were dark is because of how much wood was used to burn as fuel, light source, cooking, and it was very, very dark, and it was kind of hazy, cloudy in the Middle Ages. Well, then the Industrial Revolution came on, and we kind of changed our fuel sources, but still, used a fuel source that produced a high amount of air pollution. That was coal. So we started using coal in power plants to produce mass amounts of metallic goods and all sorts of other things, and that actually had a lot of smoke cover over cities as well. So kind of those two places, those two major time frames where we saw one of our largest, I should say, problems with air pollution, at least back in the day. London specifically has had the most problems with it, at least in the past, dating back to 1850s, where we had a coal fog that kind of sat over top of the city of London, and for a few days. Let me go back and see how many days it was. It doesn't say how many days, sorry, but it does say it killed in 1880. Prolonged coal fog killed estimated 2,200 people. Then it says in 1905, a physician used the word smog to describe this deadly mixture of smoke and fog that afflicted London. So that was our first term of the word smog. And then another episode, 1911, killed more than 1,100 Londoners. And then even in 1952, the even worse yellow fog lasted for 5 days, killing 4,000 to 12,000 different people that lived in London. And then finally, in about 1956, British Parliament decided to come up with the Clean Air Act that actually, reduced some of those disasters from there on out. So that was kind of took them, how many years to figure out, oh, maybe we should stop, maybe we should put some regulations on what we're producing in our industries in our cities. So that's one episode, but we're not excluded from our bad case studies as far as the bad old days. Even in the United States, we've seen problems with air pollution. And the first documented one was in 1948 in Donora, Pennsylvania. And what happened in Donora was it occurred in October of 1948. And the Donora sits in the Monongahela River Valley south of Pittsburgh. So kind of sitting in between two peaks. And what happened is that the pollutants came from coal burning factories, steel mills, zinc smelters, sulfuric acid plants, and actually became trapped in a dense fog that laid stagnant right over top of that valley for 5 days. About 6,000 of the town's 14,000 inhabitants became sick. Only 20 of them died, but 6,000 sick is a lot. And in 1963, high concentration of air pollutants in New York City actually is a very similar thing. And it says that incidents killed about 300 people and injured thousands in 1963 from the New York City high concentration of air pollutants there as well. So it is also a global problem now too, because the Asian brown cloud that we talked about in our case study affecting not only those areas over in Asia, but as well as many areas throughout the world as it moves from place to place. So let's take a look at some of the pollutants that we're talking about. And we talked about some case studies. Let's talk about some pollutants that actually do have the impact on us. We have two different types. The first one are primary pollutants. Those are harmful chemicals that are emitted directly into the air by human or natural sources. And then we have secondary pollutants, which is where those primary pollutants recombine in the atmosphere, mostly with hydrogen, possibly with a little bit of the water molecule when it's broken up, and actually form together to make even more harmful or new harmful chemicals. The good news is that in most of our developed countries like London and the United States, we've realized in our industrialization times that, hey, our air quality is important. It can have major damaging effects on our population. Let's do something to clean it up, and we have done that. The bad news comes from our developing countries like China and India, where they're still developing huge, and they're kind of in the middle of their industrial revolution, and that's causing major problems for them, and that's where we need to really focus on the most, as well as the indoor air pollution problems, which we'll talk about next section in chapter 18-3. And the problem with that is that a lot of people don't have very good ventilation in their homes, so that indoor air pollution becomes a larger threat in developing countries because of their lack of ventilation and proper heating systems for their homes. So let's talk a little. So there's a little image here for you to show you some of the different types of primary pollutants versus secondary pollutants. It's probably very key that you know the difference between the two and examples of the difference, examples of each type, because of the fact that they might come up and ask you that on the AP exam. First of all, it shows you the different sources: natural, stationary, and mobile. All of them producing these primary pollutants, which are sulfur dioxide, nitric oxide, nitrogen dioxide, carbon dioxide, carbon monoxide, most hydrocarbons, and a lot of different just suspended particles that you can inhale and cause problems. When those recombine with the water vapor in the atmosphere and the hydrogen in the atmosphere, you get things such as sulfur trioxide, nitric acid, sulfuric acid, a couple of other different things, ozone, peat pans. We'll talk about some of those in a little bit and some specific problems that they cause. But those are some of the primary pollutants, and as they recombine, some secondary pollutants in the atmosphere. So let's take a look at each of these different ones, and we're going to kind of hit and then talk about what kind of human health problems they cause too. The carbon oxides, which include carbon monoxide and carbon dioxide, most sources come from motor vehicles or burning of forests, grasslands, either tobacco smoke or open fires. And their human health impacts comes with headaches, nausea, mental impairments, collapse, coma, or even death if you're subject to those chemicals at very, very high dosages and for long periods of times. Chronic exposure, which is long-term exposure, maybe not in huge increments, but long-term exposure, and could cause heart attacks and even lung disease from these two types of chemicals. Let's take a look at the nitrogen oxides and the sulfur dioxides. And nitrogen oxides are nitrogen oxide and also nitric acid, which is the secondary pollutant formed when it recombines with hydrogen in the atmosphere, and also with the water molecule recombines to make nitric acid. The sources are auto engines and coal-burning power plants. And this is our major one that causes acid rain or acid deposition. It also contributes to photochemical smog, which we'll talk about in a little bit. And its human health is also irritation of the eyes, nose, and throat. If you're exposed to this long-term, it can cause asthma and also bronchitis. So those are some of the human impacts caused from this type of chemical. Let's take a look at sulfur dioxides, which is, again, sulfur dioxide, and also sulfuric acid, which is the secondary pollutant caused by that when it recombines with water vapor in the atmosphere. And the sources are electric power plants and industrial power plants, as well as oil refining and smelting. And this is our major contributor to the Asian brown cloud, and it can cause major negative impacts, as well as contribute to photochemical smog as well. So let's take a look at particulates. Particulates are basically suspended particles in the atmosphere, and they come in two different categories, fine and ultrafine. The most harmful is the fine. They're the largest. They have a diameter of greater than 10 micrometers, and ultrafine are less than 2.5 micrometers. But those are some bad things too. They can cause some irritation to your lungs and respiratory system as well. And the human health, again, is irritated eyes, nose, and throat. Also, depending on the particles that you're ingesting, could cause bodily mutations, reproductive problems, and cancers, and possibly premature death if inhaled at high dosages. Let's take a look at ozone. Ozone, we've talked about, is a really great thing if it stays in the stratosphere. If it doesn't stay in the stratosphere, it's at the troposphere, we're in a lot of trouble. And again, its sources are photochemical smog, and the human environmental impacts are coughing and breathing problems, lung and heart disease, and there's many other ones that we haven't really even discovered yet, but they think that ozone does cause a lot of problems. Now let's look at VOCs. These are mostly produced by natural sources. They are hydrocarbons and terpenes and methane gases. Again, sources are natural plants, wetlands because of the decomposition process, and termites because of their decomposition and their waste excretion as well. And cows belching, producing methane, landfills, again, through the decomposition process. So a lot of this volatile organic compounds are really from digestion and decomposition and plant death. And so that's really where we're seeing a lot of those. And the human and environmental impacts can be even leukemia, blood disorders, and immune system damage. So who knew that nature could have some sort of large negative impact on us just by itself without our help? And then let's take a look at the chemical reactions. I know this is not a chemistry class, but again, that's why you took chemistry as a prerequisite, so that you can be better skilled in your use of reactions and types of reactions. A lot of these are combination reactions. So you're seeing carbon monoxide. There's not single placement. It's not combustion or anything like that. They're all combination reactions, and we have two molecules of carbon plus 2 molecules of oxygen, or just 1 molecule of O2 since it's a diatomic element, and you get 2 CO or carbon dioxide molecules. For carbon dioxide, it's a carbon atom as well as oxygen on its diatomic state, and it recombines with CO2. Nitric oxide, you have nitrogen as its diatomic state as well as oxygen recombined to make 2 molecules of nitric oxide. Nitrogen dioxide, you're taking 2 molecules of nitric oxide, and then you combine that with its diatomic form of oxygen, and you get 2 molecules of nitrogen dioxide. And finally, you combine 1 molecule of sulfur with oxygen in its diatomic state, and you get 1 molecule of sulfur dioxide. So those are your chemical reactions, all combination reactions. Definitely should know those. Should come pretty easy to you since you've already had chemistry. All right, so let's take a look at detecting air pollutants. How do scientists actually detect these? Well, they can use chemical instruments to actually detect the particles and the makeup of the atmosphere at that specific time, at that specific elevation. Also, we can use satellite imagery like you saw in our beginning, our Asian brown cloud satellite image. You can see where air masses are, how kind of clear or thick or dirty they are. You can also use nanotechnology to detect air pollutants to get more of the fine particulate matter. And also we can use biological indicators, which are lichens. And there is a whole little science focus section on page 475 on lichens, which I think are kind of interesting. They are very, very primitive organisms that absorb air and use the moisture in the air as a source of nourishment. And they are really good indicators, specifically a couple of them called old man's beard, which is Usnea trichodea, and then which is the picture that actually this is the one on the left here. That's old man's beard. And then on the right one, the yellow Avernia lichens, and they actually sicken or die in the presence of sulfur dioxide, even if the pollutant originates from far away. So, for instance, your book talks about an example in Isle Royale, Michigan, which is where Michigan's where I'm from. In Lake Superior, it's more north than I've ever been, but an island where no cars or smoke has ever intruded. They actually used Invernia, the one on the right, the lichen, to actually point the finger northward to coal-burning facilities at Thunder Bay, Ontario. So those were dying in Isle Royale because of the air mass and the flow of those wind patterns from Thunder Bay, Ontario, all the way down to Isle Royale, Michigan. So I just thought it was kind of interesting. You can use biological indicators as a sign for air pollution. All right, so let's look at another case study, and this is on lead. And why are we talking about lead with air pollution? Well, lead can move through the atmosphere very easily. So lead is a highly toxic pollutant. Again, it is an element, but it does not break down the environment because it's naturally an element. You can't get any more elementary than an element. And the sources are leaded gasoline, which we banned in 1976 and was actually phased out in 1986, and also the use of lead-based paint. And some of the most human health and environmental impacts are on children. Because a lot of times, pre this time, we were using lead-based paint to paint our homes, which we were using lead-based paint to use on our action figures and toys that we would give to children. And the problem with this, where we saw the most human health and environmental impact on children, is because actually lead itself, when ingested or mixed with a couple other things, actually tastes sweet. So when children would bite on their toys, it tastes sweet, and they'd keep wanting to bite on them. And if you had paint in your house that was kind of chipping, kids would chip paint off the walls in their cribs and actually suck on them and get the sweet flavor out of them. That would just be ingesting a toxic chemical that they didn't even know about. And so we saw a lot of very damaging cases in children, pre this time, before it was banned in 76. So that is kind of one of those scary thoughts there. We have seen reduction of lead, and the biggest two reasons is because we don't use unleaded gasoline anymore here in developed nations, or unleaded paint. There are still problems, though. I remember this was a while ago, in 2007, there was a huge recall from painted toys that were coming out of, I think, a third world nation, and they had to recall those toys because the paint they used had lead in it. It was not unleaded paint, it was leaded paint, and so that could have caused very, very big problems for children here in the U.S. as well as other nations that purchased those toys. There's also a global ban on lead in gasoline and paint now, so we shouldn't have that problem anymore, but that was our problem with lead back in the day. Again, it's still happening in the environment. So lead poisoning and prevention, we obviously phased out gasoline worldwide, phased out waste incineration, which is still a problem as it gets in the atmosphere. If you burn old toys or you burn old things that have lead in them, then you're putting that lead in the atmosphere, which then brings us to why it's in this chapter. Ban the use of lead solder, which holds things together. Ban the use of lead in computers and TV monitors, which we have not done. Ban lead glazing for ceramic ware used to serve food, which could actually chip away and be ingested over time. Ban candles with lead cores, which I don't think we use that too much anymore. And also test blood for lead by age 1, so we know what to do if there's any danger of lead poisoning. Also for control, replace lead pipes and plumbing fixtures containing lead solder, remove lead paint and leaded dust from older houses and apartments, which we should be getting there hopefully sooner than later. Sharply reduce lead emissions from incinerators, remove lead from TV sets, computers before they're put in the incinerator or for land disposal. Test for lead in existing ceramic ware and used to serve food. Test existing candles for lead. Wash fresh fruits and vegetables, which that air mass could condense lead on top of. All right. Let's take a look at also burning coal producing industrial smog. So that's one of our biggest contributors to air pollution. Industrial smog, mostly made up of sulfur dioxide, carbon monoxide, and carbon dioxide. Again, we've seen a reduction of this smog in urban cities in the United States because of our air quality, which we'll talk about at the end of this chapter. But unfortunately, China does not have such regulations at this time, and we've seen a lot of human deaths caused from that smog in that Asian brown cloud. Let's actually talk about how this actually forms from burning coal and oil, since that's where we're seeing most of our industrial smog come from. Let's talk about the sulfur part. So sulfur isn't coal and oil, both sources. As that is burned, it comes out as sulfur dioxide. It combines with oxygen in the atmosphere to make sulfur trioxide. As it gets further and moves and actually combines with water vapor, it becomes sulfuric acid, and then can also recombine with ammonia in the atmosphere and can become ammonium sulfate. And again, as sulfuric acid, that can also come down as some acid deposition as well. Carbon, on the other hand, burns off, and as it's burned, it becomes carbon dioxide or carbon monoxide, and that's a very simple molecular change for carbon. All right, let's talk about photochemical smog and kind of end out this section today. Photochemical smog, its composition is actually made up of both primary and secondary pollutants, and its sources mostly come from the exhaust in the morning from commuters when it's kind of cool and cold out, and that those pollutants kind of get stuck up in that air mass as it's sitting above the earth as they're commuting. VOCs plus nitrogen dioxide plus a little bit of heat and also sunlight yields this photochemical smog. So there's the equation for photochemical smog right there. Might want to jot that one down. Ground level O3 or ozone, other photochemical oxidants and aldehydes, other secondary pollutants also kind of contribute to photochemical smog that aren't really shown in this equation. And we had some major human health and environmental problems from photochemical smog. Let's see if I can find some of them for you today. It says, there it is. As traffic increases on sunny days, photochemical smog dominated by ozone usually builds up to peak levels by late morning, irritating people's eyes and their respiratory tracts. And a lot of modern cities have some photochemical smog, but it's much worse and more common in cities with sunny, warm, and dry climates such as Los Angeles, Denver, Salt Lake City, that's in the U.S., Sydney, Australia, Sao Paulo, Brazil, Buenos Aires, Argentina, Bangkok, Thailand, Mexico City, and Santiago, Chile, and a few others as well. So those are a couple of our examples of where we see photochemical smog the most. Let's take a look at how it forms. So let's take a look at there. We have our burning of fossil fuels out of our car exhaust. The nitrogen combines with oxygen to make nitric oxide, combines with more oxygen in the atmosphere to form nitrogen dioxide, which then will form PANs or peroxyl nitrates, or it can combine with water vapor and also UV radiation to kind of split some things apart, creating ozone, oxygen itself, and eventually ozone if it recombines, and then continuing to kind of reproduce and make volatile organic compounds. So those are that's the kind of the makeup of it, kind of how it works as far as it goes increasingly higher in elevation, and this is what it looks like, kind of a scary, eerie image over Santiago, Chile. All right, so let's look at several factors can decrease or increase and really have a major impact. So let's look at outdoor air pollution may be decreased by settling of particles due to gravity. So just sheer gravity pulling those particles out of the atmosphere. Rain or snow as well can pull those out and recombine with those and pull them and bring them to the ground. Salty sea spray, as that sea spray blows up, the salt water the water combines with those molecules and brings them down out of the atmosphere. Again, they then go into the water system, but or the aquatic habitats, but at least they're out of the atmosphere. Winds can blow them and kind of spread them out so they're not as highly concentrated, and also chemical reactions can use to decrease the impacts of that as well. But let's also look at the increasing of outdoor air pollution, and this is how outdoor air pollution may be increased. So we're going to talk about these ones specifically. The first one is through urban buildings. Those can slow wind speed and reduce dilution and removal of pollutants. So because wind masses are blocked by those urban buildings, that they don't tend to disperse as well and they become more highly concentrated. Hills and mountains can reduce the flow of air in valleys below them and allow pollutant levels to build up at ground level. So very similar to urban buildings, kind of blocking that flow and dispersion of those particles, causing them to sit in one specific area, in this case the valleys. High temperatures promote the chemical reactions leading to photochemical smog formation, which means that global warming could increase photochemical smog in many of the world's cities. So that is another one. Another one is emissions of VOCs from certain trees and plants. And this says most of the species are from oak species, sweet gums, poplars, kudzu, and heavily wooded urban areas can play a large role in the formation of photochemical smog as well. And then we have this grasshopper effect, which is where tropical air masses move to polar air masses. So it says occurs when volatile organic compounds and also air pollutants are transported by evaporation and winds from tropical and temperate areas through the atmosphere all the way to the polar areas where then they're deposited. This happens mostly in the winter and explains why for decades pilots have reported seeing dense layers of reddish-brown haze over the Arctic, as well as polar bear sharks in the Arctic and other top carnivores and native peoples in remote Arctic areas have high levels of toxic pollutants in their bloodstream and in their body. So because that's the way that those air masses move, thinking about the Hadley cell, Ferrel cell, and the polar cell moving those air masses towards the poles, that's where we're seeing some of that. And the last one today is temperature inversions. This can cause pollutants to build up in high levels during the daytime. The sun warms the air near the Earth's surface. Normally, this warm air then, and most of the pollutants can rise to mix and disperse the pollutants with the cooler air above it. But under certain circumstances, the layer of warm air can temporarily lie on top of the cooler air near the ground, causing this temperature inversion to cause those particles to stay trapped near the Earth's surface and really do some damage to people. And we see an image of this right here where you can see two things happening. One is there's two, and this usually happens because those mountain or building barriers where that cool air is kind of sitting there. There's an inversion layer where warm air mass is just sitting there. There's no convection cell moving it around. And so that, all those pollutants that are being produced by industry and people are being sat there in that lower troposphere, causing some impacts on those people. Now, if there is not as many barriers, there can be a sea breeze if it's near the coast that can actually blow that away. So even though that descending warm air mass is there and causing that sea breeze and movement of air, it can be transferred away. So that way it's not having as big of a human impact. All right, that's it. That was a long one. Sorry, guys. I had to get through that one as far as outdoor air pollution. Let's take a look at indoor air pollution next time, as well as acid deposition. We'll see you guys next time.